Hi, everybody.
The broadcast is now starting. All attendees are in listen-only mode.
Hi, everybody. My name is Matt Lumstead, and I'd like to welcome you to the State of Vermont Department of Environmental Conservation Ecosystem Restoration Program Stormwater Master Planning webinar series. That's a mouthful. Today's presentation will be a case study of a completed watershed master plan for the Crosby Brook in Brattleboro, Vermont. The project was a collaborative effort between the town of Brattleboro, the Vermont Agency of Transportation, which we'll refer to as VTrans, probably elsewhere in the webinar, and the Vermont Department of Environmental Conservation, which we'll call DEC, and it was to address roadway drainage and water quality issues within the Crosby Brook watershed. And we'll, a little later in the webinar, get into why we were addressing Crosby Brook. First, I'd like to introduce the presenters. My name is Matt Lumstead. I'm a civil engineer with Comprehensive Environmental. I have over 25 years of experience in civil and environmental engineering with a specific focus on drainage, roadways, LID, and stormwater. I'm a registered PE in Mass and Connecticut and a certified floodplain manager, as well as a principal here at CEI. With me today is Rebecca Balke, who's also a professional engineer with over 20 years of experience. She's worked extensively on water resource protection projects involving nutrients, sediments, pathogens, and the development of capital improvement plans to meet water quality goals. She's a PE in the state of New Hampshire and also a principal at CEI. Ben Lumstead is a civil engineer and principal at CEI with 15 years of experience in civil engineering, stormwater best management practices, design, cost estimation, construction oversight, and site inspection. He's also a PE in New Hampshire, and he's also a principal at CEI. Just one housekeeping item I'd like to note is that as attendees, you're muted, but if you use the chat pane, the little window on the webinar dashboard, you can ask questions, and those will be compiled, and as time allows at the end of the webinar, we'll address those questions. So I'm going to start the presentation now. If everyone can see it on their screen, the Crosby Brook Restoration Study, as I said, was in Brattleboro, Vermont. The project was funded by the VTrans through a transportation enhancement grant, which are master funded by Federal Highway. The key stakeholders, as I said, were Vermont Department of Environmental Conservation, VTrans, and the town of Brattleboro. There were some other involved stakeholders, the Windham County Conservation District, and some of the other environmental organizations in Vermont. Crosby Brook, as I said, is located in Brattleboro, Vermont. It is on the 303D list and is impaired for sediment and habitat alteration due to sediment, channelization, and buffer loss. It's identified as a Class B cold water fish habitat, and this project is an extension, as I said, as a project sponsored by Windham County Conservation District. There was a stream geomorphic assessment study completed in 2008. Our project started in around 2010 and got a little delayed by Irene and interrupted, but this is kind of the culmination. This presentation is our final report. So the goals of the project that had been developed as part of that transportation enhancement grant and to fulfill the needs of several of the agencies are outlined here. The first thing was, I'll get into it a little later, what the land uses and types of watersheds are within the Crosby Brook watershed, but they're greatly varied. So each of the stakeholders has a slightly different take on the project. But overall, we wanted to identify build-out areas first because the goal was for this to become a working kind of planning document for each of these agencies and moving forward with development in the watershed. Then we identify potential stormwater treatment practices, that's STPs we'll refer to throughout the presentation, for the corridor with a target on sediment. And then we properly size the STPs based on that build-out and the Putney Road master plan, which the town and the state have been developing together. Putney Road is, for those of you not familiar with the area, a fairly heavy, populated kind of industrial, commercial Route 5 and Route 9, at least in Brattleboro. And then we also identified and sized STPs for 91. This corridor, Putney Road, actually parallels 91 fairly closely through Brattleboro. And then we also identified STPs in the upper watershed, which you'll see some details of in a minute. Crosby Brook, as I said, is a cold water fish habitat, brook trout. There are two separate branches. The north main branch is approximately 2 miles long, and the south main branch is 4 miles long. They meet just about in the middle. You can see my cursor moving, of this area where Route 9 connects to 91 at the Route 9 and Route 5 roundabout. And then the last leg kind of travels through that dense Route 9 and Route 5 area before it discharges into the Connecticut River, which is over here on the right side of this map. So as I said, the watershed is kind of comprised of 3 different components. In total, it's 6 square miles, with the lower watershed being that Route 5 and Route 9 heavily developed area. You can kind of see the impervious down here on the bottom right of this picture. The upper watershed, these red outlines or sub-watersheds, you can see is largely agricultural and undeveloped. And then this study primarily focuses on this 350-acre portion of the watershed. So as I said, there are 3 distinct project areas we kind of called out. Putney Road corridor, Route 5 and 9, is the green area. That's the watersheds within that region. Project Area 2 was the Interstate I-91 corridor, which is this kind of pink-purple little sliver here. And then the upper watershed, that yellow piece. And they've all got kind of slightly different characteristics in terms of land use, but all 3 contribute, to that sediment load, which is impairing Crosby Brook. Project Area 1, Route 5 and 9, is approximately 240 acres, and this is fairly typical of how that corridor is kind of built out. And as I said, the town's been working on a master plan, and which they hope to incorporate that future development and build out and their approach for this area, because it is a major thoroughfare for them in one of their most prime development areas. And as it says, it's approximately 40% impervious. So you've got a lot of paving and buildings in this area. Area 2 is I-91 transportation corridor. It's approximately 110 acres, mainly paved roads, and you can see there's some grass areas, this rather large infield area of the 91 South on-ramp, and it's approximately 15% impervious. Then Project Area 3 is that upper watershed, is approximately 750 acres. Low-density residential, agricultural, less than 1% impervious. However, there's some fairly steep slopes in this area. It's a pretty hilly region. The Connecticut River Valley runs between some pretty big hills in this area. So that is one of the challenges we had with coming up with STPs to address sediment, because as you can imagine, anything that does get touched is, that much more subject to erosion.
Hey Matt, I'm going to jump in real quick.
Sure.
The screen is we can't see the right of the screen, and the bottom of the screen is cut off for some reason. People are sending some questions about that. So I don't know if you guys if there's some way to change the size of the screen, but we can't see anything below bullet 2 on Project Area 3 and to the right of.
All right, let me see if I can figure out what that is. There's some, maybe zoom?
Can you stretch that? Oh.
Does that do anything?
Oh, no, that changes that. Now it's really zoomed in.
That's worse. I'm not sure what that setting is. Let me see if I shrink it and then go to slide.
Yeah. No.
Well, why don't we do this? Why don't I run it from, what if I,
Did that help when you did that?
No, it did the same thing, but go back zoom out one more. I can see all the way to the bottom, but the words erosion on the right, it cuts off at I, E-R-O-I-S. So
that?
There we go. Now I can see it.
All right. We'll try and, this is running it from the actual PowerPoint itself, so you might be able to see some of the other stuff in PowerPoint, but everyone can see those slides now?
Yeah. Yep. Thanks.
Okay. So targeted pollutants and sources, I'm going to hand this over to Ben, who was one of the project engineers for the study and did a lot of the down and dirty stuff. I'm more of a director, so I do the introduction and then Jet. So without ado, here's Ben.
Thanks, Matt. Okay, so first we want to just, before we got into a detailed description of how we analyze the STPs for this watershed, we wanted to just talk about each of the project areas and what the target pollutants and issues were. So in Project Area 1, as Matt said, it's highly impervious, large commercial industrial parking areas. So what we were looking at is essentially sediment loading from winter maintenance of those parking lots and roadways. Also a little bit of a loss of buffer and encroachment from development onto the actual stream or brook channel. And then control of peak flows and potential high velocity runoff from those large impervious areas, looking at minimizing erosion within the actual brook itself. Project Area 2 was similar, looked at sediment and salt loading from the highway, and also control of those peak flows and high velocity runoff. In Project Area 3, focused a little bit more on sediment loading from bank erosion and some mass failures of the slopes and banks through those steep channels in the upper watershed, as well as sediment loading from the local roadway drainage. There's a lot of steep gravel roadways and obviously winter maintenance that goes along with that. And also sediment loading within the channel due to culvert restrictions, which kind of brings up the kind of off the subject of sediment, but wildlife passage and limited buffer also in those areas to the stream, which affects stormwater quality. So just to give you a quick overview of the what we're going to discuss here for the STPs, or the stormwater treatment practices. First, I'll go over the identification of the STPs, how we picked locations, how we came up with STP types. There were a lot of different factors involved with that. And then Rebecca will discuss in a little bit more detail the STP sizing and potential pollutant reduction. And then I'll take back over and discuss how we selected some of the top ranked STPs and how we came up with the recommendations. And then I'll give you a brief overview of not all the recommendations, but at least the top 2 for each of the project areas or the highest ranked sites. Okay, so to start out the STP identification, in looking at how we were going to select types and size them and also essentially rank them, it kind of was based on the conditions and the problems in the project area that I just described. So in project area 1, we said it was highly urbanized, and there were quite a few large open areas, large available space. So some of the STP types we looked at were bigger basins, infiltration basins, gravel wetlands, and treatment trains, which are a series of basins in a row to provide that stormwater treatment. We use the Vermont Stormwater Manual roughly for STP sizing, as Rebecca will describe later. And then in ranking, we looked at a feasibility and a cost effectiveness of TSS removal. And that's similar for project area 2 for the sizing and ranking, but we looked at different STP types for that area because it's more of a linear transportation corridor, and there were a lot of wet areas that we noticed and a lot of narrow open areas. So some of the STPs we selected were more linear type swales, and then wet ponds or filters that would work a little better in wet areas. And finally, in project area 3, which was more of an undeveloped area, we focused in on culvert improvements and crossing with the brook, as well as potential buffer issues in areas that need stabilization. And how we sized those, there were a couple different ways to do that, but really we just looked at channel width and how big the problem was, if it was erosion. And then finally, we just looked at the size and scale of the project for the ranking. So we did a little bit of different analysis in project area 3 compared to project areas 1 and 2. So for that identification of the project locations and types, we did a couple different reviews. We went out and did field reviews in the area. We also had a little detailed resource area review looking at potential wetland areas, potential buffer areas and areas to be protected, maybe where you can't do an STP. And then we looked at we did a very detailed plan review. As you can see in that bottom picture on the screen, those little tags are essentially represent where a project plan, we had a plan review to do for that area. So there were quite a few plans that we had available to us to look through in order to select these locations. So kind of the first limitations on STP types and constraints are listed here. And a lot of these were selected we decided to select potential locations based on these issues, and a lot of them were site constraints. So available space is a really big one, but potential utility conflicts in the area, especially in that more developed section of Putney Road, location of bedrock, other restrictions on the underlying soils, what type of soils they were, how well would they infiltrate versus hold water, any issues with shallow groundwater that we could see out in the field, maintenance access issues, as well as looking at land use. I don't know if you can see it too well, but over on the right-hand corner of the screen is an excerpt from the Vermont Stormwater Manual, and it's just a land use matrix which says what STPs would be good for what different land uses and development. So we use that as kind of a first level of guidance. And then we got into looking at the plan reviews, what is going on with the existing infrastructure, both on the town side of things, the private, as well as on VTRAN's property. And really, as I said, for the Route 5 corridor, project area 1, the limiting factor was really available space. So that kind of directed us to where we could locate these BMPs and then or STPs, sorry, and work from there. And so, as I said, some of the existing highway infrastructure, we had some plans on Route 91, some historical plans, as well as the Route 5 Putney Road. And what we looked at there was the drainage system involved with these as much as we could, where the outfalls are, as well as if there were any connections between town roads and private roads with the state roadways. We also looked at, as Matt said earlier, at potential future build-out involved with the Putney Road Master Plan, where, what was the intention of this area, what would be the future potential land use, as well as what would the roadways look like for the Route 5 corridor in particular. There were some conceptual plans out for roundabouts. So we looked at some STPs, how those would handle that roadway drainage and how they could potentially fit into those new plans. And we also looked at build-out areas within the town, focusing obviously in on the project areas and what constraints were on those build-out areas. And so you can kind of see on the top right corner of this slide, there's some dark gray areas within this build-out area that really don't have too many restrictions on commercial development. So those potential build-outs affected how we would size these BMPs potentially in the future and where we would locate them. We also looked at, as I said before, the resource area delineations and any potential impacts. So we looked at each STP project location and took a look at what was delineated for wetlands or other resource areas and what the potential impacts would be if we implemented a STP there, especially with permitting, which has an effect on cost. And we also looked at, for the project areas 1 and 2, we had a really good delineation of subwatershed and drainage systems on both private properties and on town roads and state roads. So we were able to kind of look at what potential subwatersheds could drain to a particular area that we selected. How big, that would really determine how big the STP would have to be. But also looking at the drainage system, how would those be diverted to get that runoff to that location? That kind of involved a lot of the potential drainage connections between some of the larger developed private properties that tie into the state roadway along Route 5. And finally, we looked at and used as a priority the location of outfalls and the condition of those outfalls along the brook corridor. And you can see in that picture the red dots are the subwatersheds that were broken out, and the yellow dots are the outfalls. So in that area, there are quite a few outfalls associated with drainage in project areas 1 and 2. And finally, for study area 3, we really just used information from the previous geomorphic assessments and took a look at channel widths and condition of culverts and other things to come up with our STP identification. So that was the major deciding factor for study area 3. And so now I'm going to hand this over to Rebecca, who's going to talk about some of the STP sizing and process.
Okay, I want to give a little bit of a background on how we did the sizing to give you guys an idea of the methodologies that we used and what we focused on in sizing these STPs. As Ben had mentioned earlier, we really used the Vermont Stormwater Management Manual for our criteria for sizing. We were focusing on 2 things. One was for peak flow attenuation, and the other was for water quality treatment. Within the peak flow attenuation, we were looking at a few different items. One is channel protection, which targets the smaller storms that are really your channel-forming storms. We also looked at the overbank protection, which focuses on a 10-year design storm and trying to detain that. And we also sized for the 100-year in terms of protecting the stormwater treatment practice. We wanted to make sure that the 100-year storm could pass through that safely, so we had to give it a nice spillway for that to happen. And then in terms of water quality treatment, we looked at a few different things as well. We looked at the water quality volume, which is the volume of water that you have to treat to remove pollutants. We also looked at a pretreatment volume to ensure that we had adequate pretreatment. For example, if you have an infiltration STP, you want to make sure that you're removing a lot of the sediment load so you don't clog that. And we also looked at recharge volume to try to mimic the conditions that might have been there before development had occurred. The tool that we used was the Autodesk Storm and Sanitary Analysis Model, and that's part of AutoCAD. You can see in the diagram here what we did is we broke the watershed up into several different drainage areas. That's these green areas with the darker green outlines here. And we used the model to calculate the peak flows and water quality volumes for each of these areas. The SSA model uses a TR55 methodology, so for those of you that are familiar with that, I'm not going to run through the details of TR55 because that would take over an hour in itself, but that's basically the background and the methodology that this model uses. So as part of that, we look at curve numbers. Part of TR55 is to establish curve numbers, which are based on the land use cover and the soil types within each of those drainage areas. We also looked at time of concentration, which is the amount of time that the rainfall takes to get to the discharge point for each of those drainage areas. We looked at impervious areas, which really come more into play with the water quality volume.
Oh,
hold on, somebody's mentioning the right side still slightly cut off. We're just going to try to fix that.
Can you guys see the whole PowerPoint, or is it just the?
I can't talk to them.
Well, they'll type something. Widescreen.
This is Elise again. It's just the very, nope, that makes it worse.
Yeah.
It's the very right edge. Someone suggested you might be on widescreen format, which might be causing an issue, but oh, go back. So it's still the right side is cut off a little bit.
Yeah, let me see if I can check the view.
Sorry about that.
Let's see, widescreen is a choice. What do you see now, Elise?
So I can, the first point, oh, that's better, but I still can't see the right edge of the slide. And that makes it, that made it a little bit better. There we go, and I can see the whole slide.
And is it big enough? Is it filling up your screen?
No, I mean, you can see the whole PowerPoint,
Yeah.
you know, but I can see the whole slide now.
Huh. Sorry, this is a new computer.
Aha.
So, I don't know what anything is.
I mean, I think this, you can see the whole thing now, so I think it's a little hard to see the actual numbers. But
yeah, I'm sorry. It's really hard when she points to something to read it.
Yeah, to just maybe, read the numbers if you're going to be pointing to anything.
Okay.
Yeah. Okay. So one thing I did want to point out when we did use this methodology is TR55 has certain design storms, which is basically just a frequency storm that you use to size practices, and we used some higher precipitation design storms that take into account, the more recent weather patterns that we've been seeing, because TR55 is kind of old for that. So it's using larger storms, basically. For areas 1 and 2, as Ben had mentioned, we really focused on the channel protection volume and the overbank protection volume. The little cutout here is right from the manual, the Vermont manual. The channel protection volume basically looks at extended detention of the 1-year 24-hour storm. For cold water fish habitats, we look at 12 hours extended detention, and for warm water, it's a 24-hour detention. And that's, obviously you don't want the waters to warm up too much before they do discharge into the stream. And then the overbank flood was the other thing we looked at. Now, I just wanted to point out in terms of the manual, this is typically used when you're looking at a new development or a redevelopment scenario and you're comparing a pre-development to a post-development condition. For our purposes, we wanted to make sure that we had enough volume, or we were looking at the volume that could detain for 24 hours the 10-year storm, but we didn't really have a pre-development condition that we looked at for comparison. So I just wanted to point that out. For sizing the basins, or the STPs, for the basin volumes, we basically use these charts here. There are some rules of thumb that relate flows and detention times and volumes together. So basically, as part of your Tier 55, you develop a unit peak discharge rate, which is shown on the left side of this curve. So you use your time of concentration, your initial abstraction that come out of the model to develop a unit peak discharge rate. That unit peak discharge rate is then used in this curve here, and we know how long we want to detain the water for. So in the case of the overbank flood, we want to detain things for 24 hours, so we would look at this curve. In the case of channel protection volume, we only want to detain things for 12 hours, so we look at this curve. And that allows us to grab the ratio of overflow to inflow off of this chart. That is then used with this curve here, once we get this ratio of Q naught to QI, to grab our storage volume ratio. And then you use these equations over here to calculate what that storage volume would be. So that's kind of the process that we use to determine how much volume we needed to treat the channel protection volume and the overbank. We basically took all of these inputs and outputs and developed spreadsheets that allowed us to do these calculations within a spreadsheet for multiple drainage areas at one time. So basically took all of those equations, took the outputs from the SSA model in terms of peaks, which is, you can see here for the peak runoff, and used those equations to calculate our volume, our storage volume. So in this example, anything highlighted in yellow was what we calculated for a storage volume for the channel protection volume for these specific drainage areas. And this is just a sampling. This isn't everything. We did the same thing for the overbank protection volume. Oh, and the OBV was an acronym that we just kind of made up. Just when you look in the manual, it's actually called the Q10, but we called it an OBV here. But so anyway, we also used the same methodology and the same kind of spreadsheet format to calculate the overbank protection volumes. Again, which you see highlighted in yellow in the end here in cubic feet. And the numbers aren't as important. I'm just really trying to get to explain to you how we did this and the tools that we use. And then we also, after looking at the peak volumes, we also looked at the water quality volume. And again, we just used the equations that are outlined in the Vermont manual, which is based on the drainage area, the imperviousness of that drainage area, and this p-value, which is a 90% rainfall event, so 0.9. And we used this equation here to calculate our water quality volume that we wanted to target to treat. We also looked at the pretreatment volume. Now, in the Vermont manual, the pretreatment volume varies depending on the STP that you're actually designing. For our purposes, where we were evaluating multiple drainage areas, we just used a 10% value. It's 10% of the water quality volume, which a lot of the STPs, that is the requirement for them. But there are a few, I think it's the gravel wetland, for example, that has a 25%. But for our purposes, we applied a 10% water quality volume to calculate the pretreatment volume area, or volume that we needed. And again, that's shown here in yellow, and the spreadsheet just really uses the equation to calculate that 10% value. The other thing we looked at is the recharge volume, and again, we used the formulas that are in the Vermont manual, and those are based on, as I mentioned previously, we're really trying to kind of mimic a pre-development condition. So it's based on the soils, and there's a recharge factor associated with each soil type, A being the most permeable soils, D being, you can see here it's waves because those are more of your clay-type materials where you don't really get infiltration. It's also based on the drainage area and the imperviousness. So using this equation, we calculated the targeted recharge volume that we wanted to achieve for each of the drainage areas that we looked at. Now, this isn't animated anymore, but it was before, so it's a little messy. But this basically summarizes how we looked at our results. So, once we went through all these different calculations, we compiled everything into one table so we could compare the STP volume, so the volume of our treatment practice, to the sizing criteria that we were evaluating and trying to target. So you can see here in the black, the STP volume meets the recharge volume, or I should say, there's basically, this one I'm comparing strictly to, in this particular example, we were looking at a few different STPs. One was an infiltration pond, one was a wet pond, and one was a gravel wetland, and these would be constructed in series. So what we look at is, does this infiltration pond provide enough recharge to meet the recharge criteria? And it did. So you can see here, I can hardly read it too. The 11,000, there's roughly 11,000 recharge volume needed, and we had over 33,000. So there was plenty of recharge volume. Then we also looked at the water quality volume, which is right here, and the channel protection volume, and compared those to the total volume of all of these STPs together. So this is the sum of these values here, and we had plenty in our proposed STPs to meet those. And then we also looked at the overbank flow volume, and in this particular case, we were just shy. The overbank volume required was just slightly higher than what we were able to achieve with the STPs that were selected, but it was really, really close. And in this case, we're dealing with space constraints, and we're really trying to fit things into where we can, based on where the roads are and how much room is available, and topography and those types of things. The other piece that we looked at was what type of land uses were in each of these drainage areas. So we were looking at, who owns these properties that we're treating. Is it mostly coming from the highway? Is it coming from private property? So you can see here where we circled, we just really broke down the drainage area to see the percentage that was being contributed from each of the different things. And in this case, we had 87% coming from private property and 10% coming from Putney Road. So it just gave us a better idea of what was being fed to these STPs. The next piece that we looked at was pollutant removal. And as Matt and Ben had mentioned, we were really trying to target sediment because that was one of the issues in one of the water quality listings that was on this brook. So for that, we used the simple method, but I just wanted to show you the table first. We relied on the tables in the Vermont manual. They outline specific removal efficiencies for various STPs. So you can see here, wet pond removes about 80% TSS. So we used these values here for TSS, total phosphorus and total nitrogen, to basically estimate the percentage that would be removed from our STPs. We then incorporated those into a model spreadsheet that uses the simple method. And what the simple method does is it calculates pollutant loads based on concentrations that were measured across the area or across the nation. So you have various concentrations in stormwater for TSS and for phosphorus and for nitrogen for various types of land uses. So I know it's hard to see here, but the land uses are listed here. We have commercial and forested and various types of land uses. We have C values here, which are the concentrations of the various types of pollutants in those land uses. And then there's an equation that you can see down here with the pollutant loads. And basically we just used this equation in the spreadsheet to calculate what the loads were based on the land uses in the drainage area. So for this drainage area, we had paved roadways, woods, and commercial. And we calculated the loads associated with that. And then one thing that we add to that that's not included in the simple method is we also add in a stand-in factor. So for, based on a lot of work that we've done in the past and our work with municipalities, we found that a lot of STPs that have already been constructed were filling up with sediment, and roadway sanding has a lot to do with that, and that doesn't always come across. There's an additional load associated with that, so we wanted to account for that. So we built into our own internal tools here an estimation from based on the impervious area of paved roadways or commercial parking lots, what that additional load from sanding could be. So the loads actually come out in the right side of the spreadsheet over here with an annual TSS load, TP, and TN. Then we take the removals that I showed you from that previous table. We enter them into our spreadsheet here. So for each type of STP, we have a removal for the various types of pollutants. And I know it might be a little difficult to read, but like the vegetated swale here has an 81% TSS removal. We use our spreadsheet. We then take those percentages. We take the loads that we calculated in the previous slide that I showed you. We apply those percent removals, and we come up with the removal over here on this side of the spreadsheet. Where we have STPs in series, what we do is we calculate the removal going through the first STP, and then we know the load that is exiting that STP, it's basically whatever's remaining, and we apply the removal from the next STP to that. So it works as a series BMP to remove, or STP to remove those. In terms of the project area 3, as Ben had mentioned, that was based more on the geomorphic assessments. And as Matt had mentioned, there was still a sediment load coming from that, and we didn't want to ignore that. Areas 1 and 2, which I just talked about, were the more developed areas, and kind of the higher priority because they're closer to the brook and, the main stem down there. But we did want to look at the areas that were identified in the geomorphic assessment as well. And to that extent, we primarily looked at, for the culverts, we looked at resizing those culverts to minimize the channel erosion that might be associated with them being undersized, but also, to pass habitat and fish. So for that, on a conceptual basis, we sized those to meet about the 75% bank full width. And again, that was really just to get conceptual cost figures and sizing for that purpose. If these are to be designed as a final, they would have to follow the guidelines that are available in the state, which are listed down here. But it did give us enough information to use it a little further in ranking and to compare things. We also looked at bank erosion areas. So there were areas, this picture on the right here, there were some areas where there was just a lot of bank erosion on the sides of the bank that was contributing to the stream here. Actually, you can see the road, and then the stream actually runs right here. So this whole area here is eroding down into the stream. And we evaluated those in the field, and we came back, and those are really, the sizing for those is really done on an individual basis based on the size of that, the slopes. We were able to come up with some different STPs to minimize that erosion from those areas. So with that, I'm going to hand this back over to Ben, and he can talk more about how we ranked these and selected them.
Okay, so we essentially did a little different ranking process for project areas 1 and 2 as we did for project area 3. So I'll go through the more detailed ranking process for project areas 1 and 2 first, and then talk a little bit about just a kind of a generic ranking for project area 3. In looking at the potential STP sites, the basins and the swales, to determine which ones should we select as a recommendation, we did a 2-phase ranking process, and it was essentially using the model results and the sizes that Rebecca just spoke about, and then looked a little closer at the feasibility of constructing those, as well as a cost estimate and a potential pollutant removal. So the first round, or the first phase, ranked all the potential sites based on a feasibility, the location, and their ability to meet stormwater standards. And then the second ranking was mainly done to look at the cost effectiveness and removal of sediment, and that was done in cases where, say, there were two very similar STPs and they were ranked similarly. Which one would be a better one to do? Or in a lot of these cases, the STP could handle overlapping subwatersheds. So how would we select one that might be a better STP for the overall area? And so in going into detail on the first ranking phase, this was the criteria we used to look at feasibility. So we looked at the proximity to the brook, sediment accumulation and removal that we calculated in the modeling that Rebecca laid out, potential ease of implementation, the land use, who owned the property, where this potential STP could go, how do these meet any standards, or how do they comply with the stormwater manual, what would the maintenance requirements be, and what would the permit requirements be for each of these. And so this one's probably really hard to read, but this is just kind of gives you an example of each criteria. We took a essentially range of priority points based on that the importance of that criteria. So say for sediment removal, if you can see down there, it's circled, there's STPs that potentially remove 250 cubic feet of sediment a year or more, they would get ranking point of 6. Whereas if you compared that to an STP that removes only from 0 to 49 cubic feet per year, it would only get a ranking point of 1. And so there's obviously a range in between the 6 and the 1, but that was kind of just an example of what we did for each of those ranking criteria that I mentioned. And what we did was we created a matrix and entered all the raw data into the matrix. What subwatersheds were handled by each STP, what was the subbasin size, calculated impervious area, how much removal per TSS, property owners, etc. And then also looked at the ability to meet the standards that we calculated. So there might have been a range. If one of the STPs could handle the overbank volume target, then that would be good, and it would be ranked higher than one that wouldn't be able to meet that. And so in most cases, we attempted to size them based on the restrictions, based on water quality, volume, and channel protection. So kind of those all ranked out to be the same, and really what we looked at was the overbank volume really had an effect on the sizing or the ranking of these STPs. As part of that process, we also looked a little more detail into the costs, and we did a conceptual cost with some contingencies, and what the components we looked at for costing were obviously under construction costs, any piping, drainage structures needed, the cost of excavation and grading, and then the overall installation of the actual STP. And over on the right-hand side of your screen, there's just some examples of costs for STPs, the different types, and then an installation cost per cubic foot or per square foot, and the material cost as well to come up with the total STP installation cost for construction. We also added in, based on those numbers, some planning and engineering costs, which would involve survey, any permitting, design, and bid and construction oversight. And then finally, we added on an estimated annual maintenance cost for each one of these STPs, and we actually applied that for 10 years. So when you look at the total costs, later on when we look at the second phase of the ranking, you'll see why that comes into play. And this is just a breakdown of the background of how we came up with these costs. So very, very rough pipe cost, $75 per linear foot for a certain size and a certain length. And then if lengths got to be higher and diameters got to be bigger, the cost might go up for those. And so similar thing for excavation, essentially economy of scale was applied to these costs. And we also added in the engineering cost to come up with that total project cost. And so here are some examples of how we applied that ranking criteria. So here the STPs are listed on the far left column, and then each criteria is listed across the top, and the actual point score that that particular STP got would be applied within that matrix. And then those would all be tallied at the end, and essentially the STPs that got the highest priority points were ranked the highest. And so that's how we were able to select, both for areas 1 and 2, what were really the top STPs and what would have the best feasibility. But as I said, we also wanted to look at a second phase as to if there were very close STPs or overlaps, how could we look at potential benefits and long-term costs for these? So this was a little more detailed analysis of the costing. And what we did was, for the criteria, we took just the BMP cost that we talked about, and then the pollutant removal that Rebecca described in the modeling. And we used that ranking criteria to come up with, as I said before, a 10-year pollutant removal. So each annual removal, we just multiplied it by 10 to come up with how much removal would take place potentially if everything stayed the same in the subwatershed and that BMP or STP was maintained. So that its efficiency was maintained throughout that 10-year period. And then we essentially added the 10-year BMP maintenance cost. So each year, that cost got added to the total principal cost. And we came up with $1 per ton of sediment removed over that 10-year period in order to select our top 2 STPs per area, or the most cost-effective. And in general, those ranged over the 10-year period of between $4,000 and $5,000 per ton. Which is pretty high, but sediment weight in the ton are pretty big, so there's quite a bit of benefit to those. And so as a ranking result, the final ranking results here show the top 2 identified STPs for Project Area 1 and for Project Area 2, and what those costs were. So they're probably hard to see, but for the first STP, the cost was about $4,500. And for the second one in Area 1 was about $4,800. For Project Area 2, the cost was around $4,100, and then $4,900 for the second ranked STP.
And that's dollars per ton.
Dollars per ton, thanks. And so, as I said before, the ranking process for Project Area 3 was a little different, just because we were looking at different STPs, and we really had a detailed evaluation of the potential issues from the fieldwork, but also from the geomorphic assessments that were done prior. So in looking at the undersized culverts and what ones should be replaced, we reviewed all the ones with width less than the bank full width. And eventually, we recommend that all the undersized culverts would be replaced. But for ranking purposes, we looked at culverts with widths that were less than 33% of the bank full width. We selected those. It turned out to be 4 potential culverts. And with the understanding that those remaining undersized culverts that are under the bank full width should likely be replaced in different phases using a similar criteria. For example, the second phase could be all structures that are 67% less than the bank full width, and then finally anything that's just less than the bank full width. But it really depends on how many culverts really would want to be tackled under each phase. And so once we did that, we just came up with a cost estimate for those top 4. As a reference, it wasn't really used for any ranking. It was essentially just to summarize the ranking and what that potential cost would be associated with replacement of those top 4 culverts. And what we came up with was about $1.1 million, which includes all those previous cost parameters: engineering, permitting, design, and construction. And so for the erosion and stabilization of mass failures in Project Area 3, we really just picked the top 6 largest problem areas. So we got an estimate of each of those eroded banks or large mass failures, came up with a total square footage, and selected the highest top 6. And so that was just to provide some recommendations on these are really the big problem areas, these should be fixed first. And we came up with some cost estimates for those as well. And so now I'm going to go through very quickly the recommendations for each of the project areas. And I'm just going to detail what we came up with for, based on that ranking analysis, just the top two STPs for project areas 1 and 2. And then I'll detail a little bit of the culvert replacements and the stabilization projects that we recommend in project area 3. So for project area 1, based on the size of available space, we selected potential infiltration basins, stormwater wetlands, and multi-pond systems with wet ponds. And that really depended on what the groundwater conditions and soil types were in that area. But a lot of the STPs we picked for project area 1, as you'll see, had a lot more available space than the ones in project area 2. So on this screen, we summarize the site 1.1 and the site 1.4 for the project area 1, the routes 5 and 9. And you can see those on the right-hand side of your screen, hopefully. Project area 1.1 is down on the bottom of this figure, and 1.4 is up towards the middle of this figure. And project area 1.1 is located behind America's Best Inn, and it's really redirecting runoff from Putney Road, a private driveway, Hardwood Way, and parts of Black Mountain Road. And I'll zoom in and give you a little bit more detail on that on the next couple of slides. Site 1.4 focused on Putney Road and Route 9, and that was handling a lot of the runoff from the roundabout between 5 and 9, leading to the exit 3 on and off ramps for 91. And we located a STP on the old Bickford's restaurant lot, an area, kind of a big parking lot area that's not really being used, that runs along Route 9 and right next to the brook. And that would involve redirecting runoff from the existing drainage system on that state route to a STP to eliminate a outfall that discharges right at the bridge for Route 5 that goes over Crosby Brook. So zooming in on site 1.1, this is really in one of the more developed areas of the Black Mountain Road, Putney Road intersection. And there's some available space, as you can see in that picture there. There's a large overflow parking lot and a grass area, which could be converted over with essentially permission easements, but it's a drainage diversion. And what we looked at is doing a multi-pond system. A stormwater wetland would be to follow, but the first part in looking at being a little bit higher ground could be potentially an infiltration area, and then the second pond would be more of a wet pond area. And this would handle runoff from all of this green outlined area, and it would treat runoff that actually discharges as an outfall under the railroad to Crosby Brook right before it discharges into the Connecticut River. Site 1.4, as I said, was near the roundabout of Route 5 and 9, and this is looking at this picture. We're actually facing down towards the Connecticut River. You can see the bridges in the background, and there's a very large open area here, which provides lots of potential space. And these two STPs in Project Area 1 are really indicative of what would have to happen in this area. The available space is really on private property. There were a few, we looked at potentially infiltrating along VTRAN's right-of-way and along their corridor, but these areas could handle a lot bigger area, and because of all the drainage tie-ins from private properties, you're really handling a lot more water, and it would be hard to squeeze those into just the right-of-way corridor, as well as it's hard to say that it would be beneficial to send runoff into the subgrade of these heavily traveled roadways. So that's why we kind of, in this area, leaned on possibly getting easements to install these STPs on private property where there was available space. So for Project Area 2, which was the Route 91 corridor. These were more linear STPs and STPs that were kind of squeezed right up against the highway. And some of these areas were wet. Some of the larger potential locations actually had a lot of water and potential resource areas, potential high groundwater. So we really had to kind of squeeze these in. So a lot of them were more looking at infiltration swales, wet swales or dry swales, depending on what the condition of the median, the highway median, looked like. And then possibly providing some sand filters, which we know have been done on previous VTrans projects in the area. So we kind of focused on promoting those. So these, for project area 2, the 2 focus areas were coincidentally site 2.1 and site 2.4. And those are both on Route 91. You can see the 2.1 is over near the Black Mountain Road overpass of Route 91 towards the bottom of the figure. And 2.4 is over at the southbound off-ramp of Route 91 and exit 3. And as I said, these are essentially locating these STPs at low points and along shoulders and medians to use kind of the linear open space associated with that corridor. So this is a zoom in of site 2.1 and a picture of the median. You can see it's a pretty dry area and the groundwater seemed to be pretty high in this area. So we looked at using dry swales with sand filters or infiltration swales. And these are all located at outfalls for the highway that essentially would handle this area and would drain the Crosby Brook right next to the Black Mountain Road overpass. For site 2.4, this area was over near the exit 3, as I said, the southbound exit, and that was really looking at kind of this lower area that was a little wet, but a lot of drainage made it into that area, and so we looked at doing some stormwater wetlands and using the existing drainage and infrastructure, not really changing or redirecting much runoff, just kind of retrofitting what drainage components were there. And along the medians, we chose wet swales with sand filters because some of those swales seem to be a little bit more seasonally wet in that location. And you can see those directly discharge to the north branch of Crosby Brook, which kind of runs across a large culvert here and connects over to project area 2. So those had a pretty high impact on the sedimentation of Crosby Brook on the north branch. So now I'll get into the project area 3 and the culvert replacement location. The 4 locations were on Ryan Road, Middle Road, Black Mountain Road, and Dickinson Road. And these are just some examples of box culverts with different types of substrate and different types of embedment to be installed. And that's kind of what we focused on for the recommendation of these culvert replacements. We obviously wanted to promote sediment, more of a natural flow of sediment through the stream and the brook, as well as you can see with this perch culvert, we wanted to promote a little bit more wildlife passage. So in looking at the culvert replacement designs, we wanted to identify proper widths or make sure that proper widths were used. Proper substrate material was used to match essentially the existing channel up and down. And then look closer at doing either an embedded or an open bottom culvert, and then providing with that the correct size substrate that would have an impact on both the width and the embedment of the culvert. And then as kind of an added benefit or a best management practice to these STPs would be looking at the roadway drainage. As you're replacing these culverts, they're obviously crossing a road. And so what drainage improvements could you make to the roadway? Because a lot of times erosion and sediment make it in from the roadway at these locations. And finally, as I said, an added benefit of improving the width and preventing channelization and erosion on these banks is providing better wildlife passage with each of these culverts. And so now we're getting into kind of the last set of recommendations for Project Area 3. and that was looking at the stabilization and repair of erosion. Some of the bigger, as I said, mass failures and large bank erosion. And we identified 6 locations. 4 were on the north branch, which was the longer branch. 1 was on the south branch, and coincidentally, that was actually, it is a steeper section, but a lot of the undercutting and issues happened down kind of as a result of that channelization in the main lower branch. So there was 1 main section on the lower branch that we identified as a major repair. And so I'm going to get in detail on the next slide for some of the potential stabilization techniques, but here's some pictures on this of a different kind of bioengineered slope treatment. So this is kind of a before and after on the right-hand side of your screen of doing a kind of a wrapped treatment with willow stakes, dormant willow stakes, as well as a more structural sound toe of slope. And some of these other ones are looking at more of the linear bank erosion and the undercutting that could occur. So they're kind of a smaller in height structural support. And then this middle one was actually on the Connecticut River, and that was just to stabilize a large mass failure that really was only being held together by a few roots by trees. And so it's really intended to protect the trees there and use those to actually stabilize the slope as well. And so in looking at some of the proper stabilization techniques and what we recommended, we provided some of these details in an appendix of the report. And as I said, we looked at more bioengineered slope treatments. But with those, you want to identify the proper use of materials. So depending on the velocity and the type of erosion and type of soil, you want to look at, could you do riprap, or would you do vegetation or poor logs, or maybe a combination of all those. But in a lot of cases of the mass slope failures, you also want to select the right toe of slope. You can't always do a soft treatment right at the toe of slope, because if those could wash away, then you lose your whole STP. All of the reinforcement that went on above, all the money that was spent, could be washed away again eventually. So that toe of slope selection is critical, and the armoring of that, as well as for the vegetation and the core logs and the gabion baskets, using proper reinforcement materials and also anchoring them. So using proper turf erosion fabric or other types of fabric, geotextile fabric with riprap. So all those are very important in the long-term success of these stabilization techniques. And so we just wanted to provide that as kind of a example detail that could be used not just at these top 6 sites, but throughout the stream into the future if there are more erosion issues that come up. And so with that, we've made it to the bridges, and we think we've crossed them. And now I'd like to open it up to questions. So I don't know how you want to handle that, but fire away.
Real quick, guys, there was one question that came in while you were speaking, wondering if the slides would be available after the webinar.
Oh, okay. Yeah, if the actual, I know this is being recorded, but yes, the actual presentation could be provided. We could either put it on a website or load it on an FTP site for anyone who's interested.
Great.
We can do a PDF of it, and if you want to, we don't have our email contacts, do we?
Not on this, but were they on the flyer? They weren't on the flyer.
Why don't I type my? I'll type my. Can everyone see the chat box? Elise, do you know?
Yes.
I'll put my email in there.
Or you can actually just write it right on the PowerPoint.
Oh yeah, that's a good point.
Oh, that's true too.
Copy and paste it.
There's a question that came in Right. Did you guys compare the cost effectiveness for sediment removal between STP, culvert replacement, and slope stabilization? Would it make sense to do one before the other?
Yeah, we essentially we didn't really look at each individual culvert or STP location for an added benefit of sediment removal. We think the smallest culverts should be replaced first, but I think in an order of stabilization versus culverts, I think the stabilization would probably have the biggest advantage for handling that sediment because of the erosion issues. But the other issue with the culvert, kind of along the lines of the geomorphic assessment, is that those narrower culverts often affect the erosion that goes on, the channelization, so they too also have an impact. But as part of that analysis, we did not do a detailed sediment loading or reduction analysis between those different types of STPs. That was more focused on the stormwater basin and the wet ponds in project areas 1 and 2.
It's probably more in general. I mean, it depends on what conditions are. In this case, where we had such steep slopes and rather large mass failures of those slopes in Area 3, they're kind of expensive to address. Where the STPs in a more densely populated area were more cost effective because of the density. So in general, I would say that is probably, getting at your impervious areas that get treated and have human activity on them, they're probably the best bet, unless, like I said, you've got a steep slope situation or a highly erodible banks due to velocity or, that come out of geomorphic assessment, which, in Vermont, there is a lot more of that. There's a lot of hills. So there it may be, the tip may be more towards the best bang for the buck in terms of sediment is those areas. But I'd say in general, for more populated areas, it's the stormwater, treating runoff from roadways and developments.
Great, thanks. Okay, I got a couple more. Next question, you include maintenance costing in the rating scheme, but do you include maintenance during design and site selection?
No, I think the
design, did you say, was it design and type selection?
Design and site selection.
Yeah,
so
design.
I see what you're saying. Yes, we did.
Yeah, there's a cost component for the design, the site selection, preliminary engineering, site suitability analysis, permitting, and design. That is factored in to the ranking, to the cost for each STP.
And we also evaluated each STP based on kind of a feasibility-wise, more generally, what is an easier STP to maintain versus a harder one. That really focused in on not just the type, but also the location and how easy would it be to get to this site, and what other issues would be involved in maintaining this STP if it were, down behind in a wooded area where there's no access road, or even getting access on a private property. But as I said, the STPs in Project Area 1, there was really limited space, so that was used in the ranking, but it didn't have as a big of an effect on those ones, just because of the available location.
Okay. All right, we got a couple more. Next question is, what is the status of funding for the implementation of these recommended improvements? For any projects that have been completed, how did the actual cost compare to the estimates?
This particular project just finished. The final report was just written. And so I don't believe any of these have been implemented by the town or by VTrans. I know VTrans and the town actually are currently in the process of designing improvements for Route 5, so we'll know in a few years. I'm not sure about funding in terms of, what VTrans has planned or what the town has planned. The difficulty in this case would be need to be, because in Area 1, so many of the contributing factor is the actual private development. Unless the site comes up for redevelopment or you've got an owner who's willing to do something, then, funding's either going to be the town through some kind of grant program through DEC or other, stormwater type funding, or through VTrans as they make improvements. And really, in this case anyway, the goal of this document was to provide kind of that a stormwater planning document to go hand in hand with both Brattleboro's master plan and VTrans's design of Route 5. In terms of how costs translate out, we have done a lot of watershed studies where stuff actually gets implemented, and a study like this would feed into, say, Clean Water Act Section 319 funding, and we actually use these types of numbers as budget numbers for those for those projects. So that, while it's hard to say, well, it's hard to relate that $5,000 per ton of TSS removed to an actual project, but typically something like for a 2 or 3 acre impervious site with design and construction, at least where we've been working is running, say, in the $200,000 range. So take that one example. Is it America's Best? It's a hotel property, so it's got a large impervious roof and parking lot component. That's the neighborhood range where we've been seeing stuff come in, and that's a probably 3 to 5 acre, almost entirely impervious site. And those costs, that's strictly the design, permitting, and then construction of a BMP that meets the full water quality volume and channel protection requirements, which are they're a higher standard, but that's the goal with these, to get these waters off the impairment or to keep them off the impairment list for other pollutants.
All right. Let's see, and we actually did get Rod Francis, who's the Town of Brattleboro planning director, said that Brattleboro has not implemented any of these findings, and that the level of development is very low in Project Area 1. All applicable DEC permits are being met. I have 2 more questions that have just come in. Did you guys say that one of the site project selections occurred on private property, and how does that impact prioritization as a coordinated issue?
So I guess probably the simplest answer for that, Ben, is how much ranking did we give the fact that it was on private property, knowing that I think everyone recognizes that can be a challenge unless they're coming up for redevelopment and you've got some regulation in place.
Sure, yeah, and it wasn't, at times it can be one of the higher rankings, the landowner item, but in this case, because of Project Area 1 and the conditions of what was the available space, we didn't rank it as high as we did, for instance, compared to a cost, a maintenance access, but also really the highest were what are the potential TSS removal, and how well do these STPs meet the kind of the standards we set for sizing. So it did have a little bit of effect, but maybe only half that of what the other criteria did.
I think in this particular, and that's something that you could change when you go to do your matrix. I think in Brattleboro's case, the recognition is that there's been a slow, and the economy slowed it down more, but there's been a slow transition to a lot of the properties are older, they're being redeveloped, so there is an opportunity to to get these kind of things implemented through the design process. And there is some open space here that when, I think the town anticipates when development does kick back in full bore, that those sites, they'll be able to get these addressed that way. So in Brattleboro's case, it wasn't a limiting factor as much as it might be in other communities, say that have recent development in the past 15 years, where you're not going to have an opportunity, and therefore the site suitability is a bigger factor, if that makes sense.
Yeah, and then we have one more question so far. Are there any broad recommendations that could be incorporated into future Putney Road designs?
That's a good question. I would say, I think like I said earlier, the study itself specific to Putney Road and Brattleboro has some pretty detailed recommendations for STPs for properties adjacent to or for Route 5 itself. So I guess the answer is, incorporating what we've come up with from design, from this design standpoint in the recommendation section. If you're looking at a bigger picture, I guess if the question is as a bigger picture issue, what would be the broad approach? I would say it's improving the drainage network and instituting STPs, as opposed to, say, impervious area reduction and limiting, limiting the runoff that way.
Yeah, and I think another component of that for those STP types and stuff that we kind of looked at was any potential LID technologies, with the challenge being, if the soils aren't good, or if you don't really want to send water into that subgrade, you can still use those LID technologies, but essentially install them with under drains that after the water is treated, you can tie back into the existing drainage infrastructure. So you get that treatment, you get the TSS removal. And I think with what we've seen on the conceptual Putney Road, there are quite a few roundabouts at each section, which give you a little bit more available space. But the other challenge is utility conflict with that, that potentially run through those roundabouts and around. So it is kind of a restricted, even with expanding upon that, it turns out, some of the SDPs that for long term might meld with that design, or meld with the proposed master plan, where, say, that whole section is going to have buildings close to the edge of the road, more of almost a cityscape. You would kind of put those STPs in the back, unfortunately out of sight, but that's where the available space is, and that's kind of what meets that master plan and that build-out scenario.
Great. Well, I think that's all the questions that have come in. If anybody has anything else they want to get at before we end, but there's so Rod Francis from Brattleboro. He also mentioned that focus on DEC and partners has so far been in the upper reaches, and no VTrans or town of Brattleboro property has been part of past projects. And he asked, is there an update on when the VTrans upgrade of Route 5 will be scheduled? I don't know if you guys know that information.
Not that I'm aware of. I know it was in preliminary design, and it was, I know upgrade was at least 5 years out when we were talking, when we had our kickoff meeting, which was 2 years ago. So I think there's still some time to incorporate this kind of stuff into designs.
Great. Well, thank you guys. I think that looks like the last of the questions, and people are starting to head out of the room. So do you have any other closing comments? before we head out?
No, I just, like I said, it'd probably be helpful if you're going to go back and look at anything to just email. I put my email on that last slide. I think you can see that, right, Elise? That's up on the
Yes.
the PowerPoint.
Yep.
Probably the best way, so I apologize for my inability to adjust my screen ratio because I have a new laptop. I mean, it's not brand new, but it takes me a while to get a hold of things. So that was it.
No worries. Great. All right. Well, thanks, everybody, and we'll see you next time.
Okay, thank you.
Thank you.